It just occurred to me that I haven't been recording any of this. So anyone who's just tuning in, you've missed all of my plan for the day. So just hang on to your hats. There's the Pikachu. We want to see that. I'll put it in lock speaker mode. Last time, I've got a little bit of glare on my whiteboard here. Hold on. By the way, I got a notice, if you haven't heard from CCRI today, let's give you the hot tips, that not only are we going to be doing virtual classes till the end of the semester, but I just found out that summer 1 is going to be entirely virtual too. So I'm going to be in my home studio here for a while, and you guys are too if you're taking summer classes. That means I'm going to have to work on getting my lighting down so you guys can see clearly. Class, last time we learned about the 3 types of spectrum, and we learned about Gustav Kirchhoff's 3 laws of radiation. I'd like to start by having one of you guys remind me, what are the 3 laws of, well, maybe that's too long-winded. Maybe you can just tell me, what are the 3 types of spectra that we find in nature when we take a prism, like this prism here, and we break light apart into its component wavelengths? What types of spectra do we find in nature? Who can remind us?
There's continuous spectra,
Yep.
Emission line, and absorption line.
That's right. A continuous spectrum, emission line, and absorption line. And how about a basic incandescent light bulb, which I have one around here somewhere? What type of where are we? What type of spectrum does this bad boy produce right here? An old-fashioned incandescent light bulb.
Continuous spectrum.
Continuous spectrum, right, complete rainbow. When I think of a continuous spectrum, I think of white light, or, you know, doesn't always look pure white. Remember that a flame also produces an incandescent spectrum. It looks orange, but actually all colors are present, as I think I demonstrated last time by holding my, sorry, I'm waving my hands around to try to get the autofocus working here. It's incredibly annoying. Okay, and last time we learned a couple of really important laws dealing with black bodies or incandescent light bulb sources. We learned that there was a law called the Stefan-Boltzmann law, telling us that the brightness of a black body is proportional to the 4th power of temperature. This is really important. This is the basis behind the phrase that I like to utter, which goes, I glow because I'm hot. The key concept behind black bodies is that black bodies, or hot, dense thingies, they glow due to temperature alone, and it has no relationship to their chemical composition. So it has, so chemical, let's just say, no relation to composition. And the joke I made last time was that a steel ingot in a forge, once heated, will glow with the same spectrum as a flaming piece of dog poo. All that matters is how hot you've heated up the object, and the radiation will be predictable based on its temperature. That's kind of funny, because we saw when we looked at our gas spectrum tubes last time that if you heat up unique elements, they'll glow with an emission line spectrum, which is chemically dependent on chemical composition. Hydrogen has a unique spectrum, helium has a unique spectrum. Let's also remember that black bodies not only glow because of their temperature, but they have a peak wavelength of emission. Now, just in case I didn't show this to you last time, I'd like to go to my share screen here and share with you a very important graph from our lecture. Let's see if my computer can turn its brain on today. This picture here, pardon me, slide 76, function F5 76. This shows a family of curves known to physicists as the Planck function. And in this family of curves, we have wavelength plotted on the x-axis, and we have brightness or intensity maybe in watts per meter squared per micron or something. Just how much light is coming out is plotted on the y-axis. And you will notice that there's not one single graph, but there is a family of curves that depend upon temperature. Let's say, for instance, that we look at the temperature similar to that of an incandescent light bulb, which we studied in our lecture last time. 4,000 Kelvin is close to the temperature of a filament inside of an incandescent bulb. You'll notice that this black body is producing light at all wavelengths of the electromagnetic spectrum. In fact, I'd like to take two quick notes on this in just a moment. So black bodies produce light at all wavelengths of the electromagnetic spectrum. Do I have red light? Yes. Do I have green light? You betcha. Purple light? Sure. What about infrared? I got gobs of it. Radio waves? Well, if you keep going out here, you'd eventually hit radio waves. How about on the short end? Do I have ultraviolet? Yes. Do I have X-rays and gamma rays? Well, a very small amount, but technically there should even be some of those coming out. So what I could say then, if I stop share and then I go to speaker mode, and you guys could take this as well, black bodies produce all wavelengths of the EM spectrum, the electromagnetic spectrum. So that's note point one, if you guys are taking notes. Yes, a black body will produce all wavelengths, and this is my shorthand for wavelengths. In case you guys don't speak Greek, there's lambda, okay? Wavelengths. Black bodies produce all wavelengths of the electromagnetic spectrum, but as we saw in that family of curves, not all wavelengths are produced equally. And that is to say, there is some unique wavelength called the peak wavelength or the maximum wavelength that is produced more than others. And that was the basis of our second formula called Wien's law, which tells us that the peak wavelength of emission is calculatable using the simple formula 3 million nanometers times kelvins divided by the temperature T. And that's everything we need to know about black bodies to study planets and stars. Just going to give you guys a second here to catch up to those notes. So far, so good. This is all done by way of review. Okay. So in today's class, we're going to attempt to study the spectrum of the sun. At some point, we'll get back around to this again, and we'll try to apply these laws to the sun. In fact, that's going to be one of our homework assignments today. But first, we're going to have some lessons today about angles, and we're going to learn about diffraction and some other properties of light. Let me start by showing you a slide from my slideshow that I used to think was silly and dumb. And then over time, I started to become aware of how important it was to have a discussion about some basic terms from optics that describe how light interacts with matter. And you've got this cute little cartoon in your book that I think goes part of the way to explaining some of the various ways light can interact with matter. And it might help put some of the rest of our discussion today into perspective. Okay, so I might actually take these as notes on the board. I usually do, but let's go ahead and look here together. So here we can see light coming from a bunch of different sources and interacting with matter in a bunch of different ways. There are some objects like the sun or like light bulbs that emit light. They produce their own light. And they can produce light as a black body based on temperature, or they can produce light at the atomic scale, and they can have electrons jumping from high to low orbits and producing unique photons by the process of emission. Whether you are creating an emission spectrum or whether you are a light bulb creating a pure rainbow, these types of objects are producing their own light from their own internal atomic machinery. Once the photons leave the object, they can then go bouncing around the world, interacting with other objects. Let's talk about one of our first basic concepts. Light can be absorbed, as if by the ground. Or when sunlight heats your face on a Saturday morning when you're lying on the beach, your skin can absorb sunlight, the ground can absorb sunlight. Even at the atomic scale, which is what's happening, atoms can absorb sunlight, and atoms can absorb photons, which is how we get our third type of spectrum, the absorption spectrum. A lot of times, though, light doesn't get purely absorbed, but it also backscatters off of its surrounding objects. Let's take this as a couple of notes, because I think these terms might be helpful going forward today. So, ways in which light interacts with matter. So light can be, one, emitted, and for example, by the sun, or by a light bulb, or even by a single atom, which can emit light, all right? Light can also be absorbed, and this is called absorption. Fine, I'll just make it absorption. Okay, now I'll be consistent. I'll write absorbed. Absorbed by the ground. It can be absorbed by a planetary surface. It could be absorbed by an atom, which is sort of the same thing, just happening at the microscopic scale. Light can also be scattered. Now, this makes for a more interesting demonstration in class. But if you consider placing a red dot on the chalkboard, anyone sitting at home watching through the camera can see this red dot. But also, if I were to stand anywhere within this room that I'm in, I would also be able to see that red dot. That red dot is not an emitter of light. The red dot does not produce its own photons by temperature or by an emission spectrum. The red dot that you see on the board is backscattered light. And the light might be coming from the overhead lamps, which you cannot see, or the light leaking in through my blinds in the window. Come on, autofocus, come back to me. Oh man, I'm gonna really have to get a simpler camera that doesn't do this autofocus thing. So in order for you to be able to see that red dot anywhere you walk in the room, that must mean bazillions upon bazillions of photons are simultaneously striking the surface of that dot, and the dot is absorbing the green and the violet and the blue wavelengths, but it's kicking off and backscattering incoherently, probably, photons of red light in all directions. So usually the picture you have is you have a wall or a surface, you have some incoming beam of white light, but once the photons hit the red dot, the red photons are being scattered in all 180-degree directions as they bounce off of that dot. And there are so many scattering simultaneously, so many billions per second, so many trillions per second, that there's no place in the room you can walk to where the red dot is going to disappear. It's always going to be visible. So I think the message I'm trying to make is, most of the time when you see things, whether it's the dry erase board or me or the books on my bookshelf, you're seeing them through backscattered light. There's a world of bazillions of photons that are bouncing around and striking your eyeball every fraction of a second that allows you to see things. Scattering, therefore, is important. And it also happens at the atomic scale as well. So it can be scattered by an object. And photons can actually even be scattered by individual atoms. There's a microscopic counterpart to all of these concepts. Light can also be transmitted. Your easiest example there is by glass, right? Glass, of course, is transparent to visible wavelengths of light. But there are other types of transmission outside of the visible spectrum. For instance, radio waves, which are extremely long wavelength, are capable of penetrating through very thick substances because radio waves have lengths in excess of a meter. And remember, a meter is about this big. It's not a small unit of length. So most objects are opaque to radio light. Radio waves can pass through the walls of your room. So transmission can happen not just for things like glass, but also for different substances depending on the wavelength of light that you're considering. On the smaller end of the spectrum, X-rays and gamma rays can partially can pass through your skin because X-rays and gamma rays are usually smaller than the molecules and atoms that they're bopping into. And so very frequently they can pass through the empty space in an atom for a while before being stopped or blocked. In addition to transmission, there are some other more complex interactions between light and matter that it might be worth talking about. So light can be refracted, as if, say, by glass, or by air, or by water. And you guys may remember that our lab on Monday involved building a telescope called a refractor. Let me show you guys in my share screen a couple of pictures here. Of course, refraction is what's at work. Hold on, slide somewhere around here. When we do this Pink Floyd demo here, refraction is part of the reason why light bends when it strikes glass. And I shouldn't show you this picture to start with, but refraction is actually wavelength dependent, which is the basic principle behind how a prism works. Let me show you guys a slightly simpler picture of refraction, because unless you've taken a course in optics, this might not be familiar to you. So here you can see a white light source. There's probably some simple incandescent bulb that's at the end of this wire here. And what I believe this little piece of glass is some kind of a baffle, which is going to collimate the beam by creating a narrow slit so that a single straight line, a pencil-thin beam of light will strike the glass. You guys will notice that when the white light strikes the glass, it takes this hard right-hand turn and it bends. And this is the principle of refraction. What's happening here is that light is slowing down as it enters the thicker medium of the glass. And by slowing down, it causes the light to take a kind of right-hand turn. That's a little bit tricky to explain, but I have a slide trying to do it if you're curious. Notice that light bends towards the normal as it enters the glass, and it bends over here to the left away from the normal as it exits the glass. And here it might be nice if I explain that a little bit better. Slide 100 here is a kind of classic physics picture. You can see a ray of light coming from air, striking glass. It bends towards the normal. The normal is a physicist's way of saying perpendicular to the surface. That's some physics jargon for you there. Light bends towards the normal when it enters glass and away from the normal when it exits glass. And refraction has a lot of different funky results, right? It's why a stick will appear broken when you see it in water. Light rays are bouncing off the stick. They're traveling from the surface of water into the surface of air, causing them to bend their angle, and it makes the stick appear broken, even if it's not. There's all kinds of fun things you can do with the law of refraction, okay? The law of refraction is also wavelength dependent. And that's how a prism works. It turns out that the angle at which purple light bends is ever so slightly different than the angle in which red light bends. Sometimes they call this chromatic aberration. And this is what allowed Sir Isaac Newton to separate white light into its component wavelengths. This is very much how a prism works. So refraction is a special property that light has when it interacts with matter. And there are a few others that I'd like to talk about. In particular, one that I want to get around to today is I want to talk about diffraction, okay? Light can also be diffracted. And this is part of today's lesson. Diffracted is when light rays are bent by either passing through a small hole, which is called an aperture. You can think of an aperture as a small or a big hole, whatever. Aperture is a, I don't know, let's just call it a small hole. Or light can be bent when it's passing around a structure. And the reason why we need to study diffraction in our lectures today is because it turns out that something that's really important to astronomers, and even just being able to think like an astronomer, is to realize that there is a limit to how tiny any optical detector, how tiny a thing any optical detector can see. Your eye does not have infinite resolution. You cannot see down to the atomic scale with your naked eyeballs. And you can't even see down to the atomic scale with a microscope, although the scanning electron microscopes get pretty close. Likewise, for telescopes, which we built on Monday, there is a limit to how tiny an angle a telescope can see. And that's one of the main things that I'm here to discuss with you today. By the way, I'm also going to occasionally keep track of time. It's 12 o'clock. Okay. Because I'm not doing what I did on Monday. Let's start by revisiting an old formula together known as the small angle formula. I wonder, to any student, by the way, students, can I erase this? I got some
I have a question. Because
I'd love a question. Talk to me.
My screen's a little fuzzy. It says so right next to diffracted, it says bent by passing through an aperture. Small. I can't see what it says after small.
Oh, hole. I was trying to define aperture. I said aperture equals small hole. Aperture is kind of like a photography or a optics term. So I didn't know if my $10 vocab was going to confuse you guys here, you know. So I was just.
Yeah, how about using it as an opening, small opening?
Yeah, I like that. Thank you, Tina. Man, you should be teaching this class. Hey, actually, an aperture is just an opening. It doesn't have to be small. In the case of a telescope like the one we have at CCRI, the 16-inch Jacobi reflecting telescope, the aperture is 16 inches, which is not what I would consider small, right? Okay. Can I erase?
Yep.
Thanks, Tina. I appreciate the suggestion. Okay. Let's start by considering a couple of binary stars. I'll start this lecture by telling you all a story, an astronomy story, about objects that I like to show people when they come to my telescope. There is a star named Albireo, and I'd like to show you Albireo here on the internet. That makes for a good time when you are looking through a telescope, and it's very instructive for students. So Albireo, Albireo is, I always spell it wrong. There's too many damn vowels in Albireo. Okay. Albireo is a binary star. Let me go to images. And it's located in a constellation called Cygnus the Swan. Here's Cygnus the Swan seen against the summer triangle. Cygnus the Swan is actually an absolutely humongous constellation. It's sometimes called the Northern Cross. The tail of the swan is the bright star Deneb, and then it has 3 stars that go across. And if you follow down the neck of the swan, you kind of get to this star that you can clearly see with the naked eye, but it doesn't look that impressive compared to some of its neighboring stars. It's just a medium brightness dirtbag star that you might have seen 1,000 times without thinking about it. What's cool is if you take this star and you point your CCRI telescope at it, just a 16-inch reflecting telescope, you quickly discover that the star, that single star, resolves itself into an absolutely brilliant binary pair. Let me see if I can find a nice picture here taken by by some amateur astronomer. Here are the two stars that make up Albireo. Now, they're so close together that to your naked eye, the two dots actually just kind of merge into a single point source, and it looks like one star. But as soon as you open up your telescope and you point at it, you can see that there's not one star, but there's actually two stars there. And what's cool about the stars is they have this sort of brilliant color comparison. One is a sort of golden yellow, and the other is a deep blue. And so they make a nice contrast in the colors of stars. I should also mention that part of the reason that stars appear with different colors is because of the same properties we learned last week in our studies of our last class in our studies of black bodies. So quickly, let me go on a side tangent here. Stars tend to come in one of three colors: reddish, whitish, and bluish. And that's because stars emit light like black bodies, and therefore they have peaks in one of three parts of the visible spectrum. Function. Can you guys hear me? The, what was it, 78? Yeah, here we go. Sorry, the button to full screen is the same button to mute, so it's a little scary. Okay, here are three different stars at three different surface temperatures. A red star has a surface temperature of 4,000 Kelvin, making it essentially the same temperature as the filament in an incandescent light bulb. Its blackbody Wien peak appears somewhere on the red end of the spectrum, and the star produces much more red light than it does purple or blue light, giving the star a reddish appearance. Then there are stars like our sun. Their Wien peaks, or their blackbody peaks, show up right in the middle of the visible spectrum. And that means while they do technically produce a little extra yellow or green light, they're producing roughly equal quantities of blue light and red light. And so when you mix them all together, make the world feel good, you get a little bit extra green plus lots of blue and red, and the star takes on a whitish or occasionally a yellowish color. Then you have your insanely hot stars, which we study in our Astronomy 1020 course. These stars can have surface temperatures above 20,000 Kelvin, all the way up to 30,000 Kelvin. And that puts their Wien peak so far to the left of the electromagnetic spectrum that these stars often peak their emission in the ultraviolet portion of the electromagnetic spectrum. Of course, these stars produce a much greater flux of blue light than they do in terms of red light. In fact, technically speaking, what color is 400 nanometers, students?
Purple?
Purple. Why do stars look blue and not purple when they're technically producing more purple light? There's a thought question. I'd like to see some purple stars, wouldn't you? Yeah. Wait, did someone have an answer to my question? Let's scroll through the list of faces here. Anyone want to take a guess as to why stars appear blue and not purple, even though their peaks occur past the purple end of the spectrum?
Because purple light is fainter.
Fainter to what?
Us.
That's exactly correct, Jace. That is exactly correct. The human, I don't know if I showed you this picture last time, but the, what was the slide that I used? The color sensitivity of the human eye is not flat, but we have a dramatic change in the sensitivity of color across the visible spectrum. Jace's answer is the correct one, and you can see it here. Where our eyes are most sensitive to green and yellow, there's a rapid drop-off as you get towards the purple end of the spectrum. The human eye is an incredibly sucky purple detector or violet detector, or for any Australian friends listening, aubergine, okay? Anyways, one thing I notice when I use my, my spectroscopes is when you look at purple light from emission lines from atoms, the violet light looks almost ghost-like. You're not even sure if you're seeing it or not. So that there's something in mathematics called a convolution. What the star looks like will be a convolution of the power pattern of the human eye convolved with the light emission of the star. And it ends up being that the mixture of those two means we see stars as blue. Anyways, let's get back to Albireo. Albireo is a cool object to show Astronomy 1010 students, because not only does it demonstrate that sometimes single stars are actually not single stars, but binary stars, but it's also a nice demonstration of the color differences as related to the surface temperatures of the stars. Let's try to imagine what it's like to look through these, look at these stars with a telescope, and what types of telescopes are capable of resolving the binary pair. To get into that answer, we're going to have to first revisit the small angle formula. So let's, on our board here, let's draw a picture. I'm just trying to get this thing straight for you guys. And let's draw a pair of binary stars similar to Albireo, okay? And let's imagine that you, the observer, are looking at them from somewhere far away on Earth. We're going to do a little math problem to wet our whistles today. I'm going to draw the angular separation between these two stars using my ruler like so, and then I'll draw my physical separation. Okay. Now, the stars are separated by some angle. And in a previous class, I called this angle theta. But today, because I'm going to want to measure their angular separation in a tiny unit called arcseconds, I'm going to call the angle alpha. Remember that physicists and astronomers love to use Greek letters for angles, so that a user who's just coming into the party here will know that we're talking about an angle when we write the symbol alpha. We also have to consider the separation between the two stars, the physical separation, which I'll call S, and the distance from you, the observer, to the stars, which I'll call little d. Okay? You guys got this? Now in chapter 2, we learned a version of the small angle formula. And that version was S, the separation, is theta times d times 2 pi over 360 degrees. Where here theta was the angular separation, or the angular size of my object, measured in degrees. Obviously, degrees are a super sucky unit of angle to use when you're trying to measure the angular separation between two binary stars separated by a very tiny angle. In fact, I got a better idea. Let me rewrite this in a different way. Let me write it in terms of the angular separation between the two stars. When we did that, it was 360 degrees over 2 pi times S divided by D. Now, you guys may remember that we used this formula during one of our office hours when we were asked to calculate the angular size of the moon and the sun at both perigee, apogee, perihelion, and aphelion. Y'all remember doing that way back? Laura's nodding her head. Yeah. That was an annoying problem. Okay. Let us change variables. And let us not use the angle theta, but let us instead use the angle alpha. And I'm going to use the angle alpha because I want to convert my angle away from degrees and into arcseconds. Let's convert to arcseconds. And I'm going to do this using dimensional analysis. 360 degrees over 2 pi. Class, what units do I want in my division bar here? Talk to me so I don't feel lonely.
Degrees.
Sorry?
Degrees.
Where?
In the bottom.
And on top?
Is it going into arcseconds? No, but how do we get to arcseconds?
You know the conversion arcseconds?
No, hold on, let me find.
Oh, I thought you all knew stuff about angles. I thought you were an enlightened, civilized bunch of students that I could have an intelligent conversation with.
First into arc minutes.
All right, do you want to do it like that, Lucas? I thought you might be cool and just know how many arc seconds were in a degree.
I don't know.
3,600 arc seconds.
Thank you, Kayla. 3,600 arc seconds in 1 degree. Okay, punch them up, students. Punch those into your calculators. You're going to get a very magical number. I want it to 6 significant figures because all of these numbers have infinite precision if you think about it. 6 significant figures. I'll get my calculator too. $360 divide by 2 divide by pi times 3,600. And you get a magic number in astronomy, 206,265 arc seconds. This number, 206,265, which is for enlightened users, the number of arc seconds in a radian, appears in many different places in astronomy. That means we can now rewrite the small angle formula in a form that is superior and better for astronomers. And it looks like this. The angular separation between the 2 stars is 206,265 arc seconds times the separation divided by the distance. This is a formula that you kind of need to know if you want to talk to an astronomer. Otherwise, you can't really understand how they think about things on the sky. May I erase this conversion here? Let's rewrite this formula and solve it for the separation. Alpha times d over 206,265 arc seconds. Either one of these formulas are different versions of the small angle formula. I want to try a sample problem with it related to alberio. Okay. Share screen. In astronomy, when we see binary stars, there's 2 different senses in which we can consider them. Oh, this is the picture of alberio that I really like, actually. This is the one here. This one, you can see some diffraction spikes on it. Okay. Oh, look, this guy even watermarked it. Nice job, John Chumak. Okay, and listen, when astronomers see a pair of binary stars, they have questions. Just how far apart are these 2 stars? Is this a true binary in which the yellow and the blue star are actually revolving around each other and gravitationally bound? Or is this maybe a mere optical double, in which one star lies significantly in front of the other, but if you can see what I'm doing with the camera here, they actually just seem to be close to one another. Well, perhaps we could take the angular separation between these 2 stars, which I happen to know is 35 seconds of arc, and the distance between the 2 stars, which the internet could remind me, I think it's, I don't know, 2,000 light years. Ah, shit, I can't remember. Where's the distance to this thing? Oh, here it is right there. Oh, sorry, 434 light years. And perhaps, class, we could do a groovy sample problem where we calculate the, where's the picture I liked? We could calculate the actual physical separation between the 2 stars. Just a simple little exercise to show that we understand how to use this formula. So let's use this version of the formula right here. Find the separation between alberio A and B. Usually we name binary stars. There's an A star and a B star. By the way, we also name twins the A twin and the B twin. And I know this because I had a really cool pair of twins in my class last semester. And they were amazing, and they taught me all about twin life and what it means to be a twin. Twins, of course, are rare in people, but binary stars, twins in star life is actually very common. Roughly 50% of all the stars that you see in nature are binary stars. So if you meet some twins, I was told, you don't ask them, are you twins? Because of course you're twins. What you should say is, who is the A twin and who is the B twin? The A twin comes out first, okay? So they also have a word to refer to people like us who are not twins. They call us singletons. Okay, let's find the separation between alberio A and B. We know that they're separated by an angular separation of 35 seconds of arc at a distance of 434 light years. Now, I'd like to start off by pointing out to the class that while alpha must be in arc seconds for this formula to work, that distance and separation are both quantities of length. So all that we really need is for these guys to have the same units to work. That means I could even plug in light years if I wanted to, although I'm guessing that light years are not going to be the most appropriate unit of distance to measure between stars. What do you think would be a good unit of distance, class, to use to measure the separation between stars if we want to figure out if they are bound to one another?
Meters?
I'm sorry, Tina?
Meters?
Tina, unmute your mic and then pause and then say it, because I think we're getting clipped off there.
Meters?
The thing about meters, Tina, is meters is only about this big. And the stars are going to be separated by, here's what I'm thinking. You know, I think that Jupiter is almost like a failed star, right? If Jupiter had been more massive, it could have ignited fusion and we could have lived in a solar system with 2 suns, just like in Star Wars. That would have been kind of cool. So we measure the distance from our sun to Jupiter in astronomical units. And I know the solar system is about 100 astronomical units across. So I was thinking meters would be too small, because if you come up with 65 million billion trillion meters, that's not going to really stick to the walls of your brain in a way that's understandable. But I'm thinking if we calculate the distance between these 2 stars, if they turn out to be around 100 AU or so, then I would know that they were about a solar system's diameter apart, and that would make me suspect that they are a bound binary. Do you follow my logic there?
Mm-hmm.
Whereas if they turn out to be 5 billion AUs away, then they're not bound. And if they end up being 3 meters apart, then something catastrophic is about to happen. Okay, so eventually I want to get to AU, but let's just calculate it in light years first, because you know, we're separated from our closest star, Alpha Centauri, by 4 light years. So let's see if we're less than 4 light years to start. Okay, so I'm going to plug in here 35 arc seconds times 434, light years divided by 206,265 arc seconds. Someone want to punch that up for me real quick?
0.07.
Light years. They're clearly less than a light year. Jace, how should we do our conversion to astronomical units? I think we're going to need at least 2 bars to do that.
Light years to kilometers.
Yep,
And kilometers to AU.
I love it. Jace, do you have those numbers memorized by any chance?
150 billion kilometers in a light year?
No, it's 9.5 trillion. That's something from our 1020 class. 9.5 trillion kilometers per light year. How about kilometers to AU?
Is that 150 billion?
Yeah, that's right. Okay, punch him up for me.
Shouldn't 150 billion go on the bottom?
Yeah, I was just testing you to see if you could catch that. Clearly, you passed the test, so. Okay. You guys punching? Who's punching? Nice. What'd you get, Lucas? Wait, where? Oh, I lost you. 4,400, says Lucas. Cool.
I got that too.
All right, that's good. What do you think, students? Does 4,000 astronomical units suggest that Albireo A and B are a true binary? Or are they just kind of,
Too far away.
you'd say, too far away? The first time I did this calculation, Lucas, I thought 4,000 light years meant they were too far away. But over time, I've started to think about things. In particular, I started to think about the reservoir of comets surrounding our solar system known as the Oort cloud. Bear with me here. There are two types of reservoirs for comets.
A few moments later.
Okay. By the way, for those of you just joining us, after hours, I had a malfunction with my computer where the battery ran dead. So this recording is probably going to be chopped in two. All right. I'll figure that part out later. But hey, whoever said that, whose idea was that? That was a good idea. Thank you.
He deserves bonus points.
And bonus points shall be rewarded to him in Astronomy Valhalla, where the Vestal Virgins will shower you with wine and supernova juice. Okay. All right. Anyways, before I say something really stupid, let's go check out the Oort cloud. Okay, so here we are. We're about to take a look at the Oort cloud. And the Oort cloud is a reservoir of long period comets. And you'll notice that this picture is sort of nice here. It shows us a comparison between our own solar system and the distance to Alpha Centauri. Come on. What's going on here? We don't need little pictures. We need big pictures. Okay. Here's our sun. Here's the planets of our solar system. And let me just go into this mode here. Over here, you can see the star Alpha Centauri 4 light years away. By some estimates, the reservoir of long period comets is a spherical distribution of cometary objects that can extend from 1,000 astronomical units, according to this, almost all the way to Alpha Centauri, almost up to 100,000 astronomical units. Now, I've got to imagine that Alpha Centauri has its own Oort cloud. That means that our Oort cloud and Alpha Centauri's, we must be sharing spacey ice balls together. It's kind of like our macrobiome or something. Some of these objects must occasionally orbit Alpha Centauri. Well, actually, this is a logarithmic scale, so that's not entirely accurate. Alpha Centauri's Oort cloud is also, there's a difference between, right, 10,000, 100,000, and a million. But in any case, the point I'm trying to make, Lucas, who I was talking to before the computer died, is at 4,000 light years, it could be that these two stars are actually gravitationally bound to each other. However, if they are only loosely gravitationally bound, and they must have periods of tens of thousands of years or more.
So would other stars like swing between them?
Well, possibly. The stars can have close gravitational encounters. Remember that the collisions are very rare. In fact, let me explain why the answer to that question is a resounding yes. If I go back to the picture of Albireo, it turns out that the yellow star that you see there, Albireo A, is not actually a single star, but it's actually itself a binary. So in other words, this is a binary in which one of the stars is another binary. This leads to a very funny joke in astronomy, which goes 3 out of every 2 stars is a binary, okay? And this situation here encapsulates that perfectly. By the way, why can't I see the 2 stars there? You may already know the answer to the question. What is it? How come the yellow star looks like a single star, and I can't resolve the binary pair.
They're too close together.
Yeah. Whatever the resolution of that telescope was not allowing us to separate the two binary components. And this kind of gets me to my last point, the last little module I have for us today. How close can two objects be and still be resolvable by an optical system? That turns out to be limited by a property called diffraction. Let me get back to share screen here for a second. Diffraction is the bending of a wave as it passes through an aperture or opening, as Tina suggests. Oh shoot, I gotta get my astronomy lectures back here. Light and telescopes. Okay. Let me show you guys a little picture of diffraction. You'll remember that light waves of any type have a couple of different properties. Oh shoot, I forgot what that slide was now. Light is a wave, and waves have properties like refraction, and they also have a property called interference. Interference is the adding and subtracting of waves when they occupy the same space. And another property that's closely related to interference is diffraction. So let's talk for a quick second about an interference pattern. If you make waves on a string, when a crest strikes a trough and they overlap in space, the positive crest and the negative trough cancel each other out to make a zero. When you make waves on a string, if two crests line up, you will temporarily get a bigger crest where they overlap. And waves on a string, of course, are one-dimensional, but it's possible to make a two-dimensional wave pattern using something called a wave tank. In a wave tank, you take a fish tank and fill it up with water, and you take two mechanical needles on two motor arms, and you have the motors use the needles to poke small dimples in the water as if you were dropping pebbles over and over again into the water. Now, if you illuminate the wave tank from above, anytime you have a crest of a wave, the refraction causes a bright fringe, and refraction causes a dark fringe wherever the wave has a trough. So you can see the crests and the troughs of this wave as bright and dark fringes. Can you guys see these patterns of gray that radiate out like spokes? Say yes. Okay. Those are regions of destructive interference. Here's a little computer animation of it. You can see our bright crests and our troughs are canceling each other out to make these sort of destructive interference nodes. And by the way, this occurs not only in water waves, but also in sound waves. Here's the design of a Greek amphitheater where two thespians could be having an argument on stage. Notice that they've designed the aisles of the auditorium in the same pattern that you saw destructive interference for two mechanical waves there, two water waves. And that's because sound is a wave, and in amphitheater design, you want the hallways to be dead zones where the voices will kind of cancel each other out, and you want to create seating where there's constructive interference so that the arguing actors can amplify each other's voices when they get up to the top of the hall there. So we can see interference patterns in all types of different waves. It turns out that diffraction is intimately related to interference in a complicated way. And I'm going to give you a kind of quick and dirty version of it because of time here. But diffraction is basically the bending of a wave as it passes through some kind of an opening. And diffraction happens with water waves and with sound waves and, of course, with light waves. Let's say that you were down in Newport Harbor and you were watching a big cruise ship come through the bay there, and you could imagine some large planar waves sort of coming off the wake of the boat. If these long parallel waves were to strike an opening in the sea wall, the waves would bunch up as they pass through the opening in the sea wall and cause them to become circularized or bent. And if you take a look at this picture, you'll see that the amount of bending that a wave gets is related to the size of the hole that they are passing through. In the top picture, the aperture or the hole in the wall is roughly the same length as the wavelength of the waves. And when the hole is the same size as the wavelength of waves, or if it's smaller, you get lots and lots of diffraction and lots of bunching up. On the other hand, if the opening in the seawall is really large in comparison to the wavelength, then mostly the waves pass through unmolested, but you can still see that there's a tiny little bit of diffraction, a little bending of the wave as they bunch up around the edge of the seawall. And diffraction not only occurs in water waves and in sound waves, but also in light waves. Now, this is a picture that might be a little difficult to understand. Light is passing through a tiny pinhole, and it's light from, say, a star or some other point source. But instead of all the light from the star appearing on the other side of the pinhole at the central disk here, you can see that some of the starlight has been scattered off to the left and the right in these interference, or we call them diffraction fringes, dark destructive fringes, and bright constructive interference fringes. Now, I have a really cool demo that I like to do. I'd like to do a demo or two per day, so I'm going to attempt to do a diffraction demo here in our class. This could go over great or bad. Let's see how it goes here. I'm going to erase. And I've got in my hands here a couple of lasers, okay? Let's see if we can focus this laser dot. I'm gonna make a mark to see if it stays focused. This is just for me to tell if I'm in focus or not. Okay. First of all, it looks a little bit more smeared out on the camera than it does here, but you'll notice that the laser dot that I'm projecting onto the board is not a perfect point. There's a little bit of a disk that it's made by its own diffraction. And if you're here in the room, you can even see a little bit of scattering around it related to diffraction. What I want to do next is I want to pass it through a small opening or small aperture. So let's get this camera to focus. Oh, this autofocus is driving me crazy. Come on, autofocus. All right, well, actually, you guys can see here that I have an opaque screen in which slots of, boy, there's a couple of weird light scatterings going on there. I've got here an opaque screen in which a number of different slots of different widths are being passed through. Oh, look, you can see your faces in there. Now, you would think that if I passed a beam of laser light through one of these narrow slots, that the light would just appear as a single dot on the other side. But let's see what happens if I do this. Hold on, guys. I probably should have practiced this before I tested it out, but that's me. Okay. Let's see if we can do this here. Can you guys see that? It's hard for me to. Oh, there we go. That one's good.
Yep, we can see that.
Yep.
Can you see that there's not one dot, but there are multiple dots there?
Yeah.
Yep.
I mean, what the hell is going on? How does passing a single collimated beam of laser light, what makes it pass through this tiny slot and appear not as one dot, but as a whole sequence of dots that are interfering with each other? Well, that's a long and complex story of physics. You're witnessing something called a diffraction pattern. When light bends as it passes through an opening, the light interferes with itself and it creates an interference pattern. This is the picture that you were just looking at in real life, shown by having a laser pass through a tiny slit. Instead of the laser dot appearing as a single dot, it appears as a bunch of constructive and destructive dots. Now, at this point, you guys are probably thinking, what the hell am I learning about, and what the hell does this have to do with astronomy? Well, it has to do with astronomy for the reasons that when you take light from a star and you pass it through a telescope tube or an opening, not only does some of that light appear as a little fake disk, but also some of the light blurs out into these diffraction fringes. And what happens is if you have two stars in a binary and you try to image them, they'll be separated on the left by some small number of arc seconds. But here we can actually see the two little diffraction disks of the star side by each. As the stars get closer and closer together, their diffraction patterns will begin to overlap. And instead of seeing two stars, now you're going to see this lumpy peanut-shaped thing. And eventually, if the stars get even closer, their diffraction patterns will overlap so much that the two stars will appear as one and they will blend together. In other words, the big takeaway message that I was trying to explain is this. This optical effect called diffraction limits how tiny an angle an eyeball or a telescope can see. Now, this is my last module for the day because I'm just about out of time, but let's put it up on the board and do a quick sample problem, and then we're done. Okay. So here are the notes that I want you guys to have in your notebooks related to diffraction. Come on, camera. This camera loves to focus really, really close for some reason. And I'm going to fix this. I'm going to figure it out at some point. I'm trying to stay stationary. There we go. Diffraction is the bending of a wave as it passes through an aperture of diameter d. Can you guys read that? I keep grabbing the wrong color here. Diffraction, the amount of diffraction depends on wavelength. That's the first point that I'd like to make. And the second point I'd like to make is the diffraction pattern limits how tiny an angle, which I'm going to call alpha min. Diffraction patterns limit how tiny an angle alpha min my detector can resolve. And by detector, I could mean the human eye, I could mean a telescope, or even the camera that's allowing you to watch this lecture today. This camera has a diffraction limit, just like any other optical system. There is a formula for the diffraction. Are you guys able to read this? My handwriting isn't the best right now. Okay. So here is our formula for the diffraction limit. Alpha min, the minimum angle of resolution, is 250,000 arc seconds times the wavelength of observation divided by the diameter d. All of that spiel that you just learned was a big setup for you to learn this formula. Why do you need to know this formula? I'll tell you why. When people come to my observatory and they look through the telescope, the first thing your grampy is going to say to me is, "Hey, bud, can we see the American flag on the moon?" And I say, "Well, no, not really." And he says, "Well, why not?" And I say, "Well, because you have to understand this telescope has a diffraction limit." And as soon as I say that, his eyes gloss over and he's no longer interested in anything I have to say. It's technical, it's complicated, but diffraction is what limits how time. This is why you cannot see the American flag on the moon. All right, and we'll do a demonstration of that in just a second. Have you guys got these notes here? Because I want to erase. Lucas, it looks like you're still writing. I can't hear you, but.
Give me like 20 seconds.
Sure. All right, I'm erasing. We're doing one sample problem. Oh,
Wait,
sorry.
Okay, yes. All right, you're good.
No. Talk to me. I can give you time, pal.
No. It was on. It was only because I like for some reason like it switched to my screen switched to Jace, and then it was switching to Angel and then to Laura, and it just kept like bouncing, and I couldn't find you, and I was like, uh-oh. I got them all
What
down.
to do?
All good.
Go to locked speaker mode. Find my little face. Double click on it, and make sure that you're not in gallery view, but you're in speaker view, and you should be able to lock it on me. If you double click my face, a little green box will illuminate, a little green line will illuminate my box, and then you'll know you're in locked speaker mode.
Okay, yeah, I saw it.
All right. Let's try a sample problem with the diffraction limit. The CCRI telescope, the telescope that's in our backyard, well, I guess now none of us are at campus anymore, but it's a Meade LX200R. It's a Schmidt-Cassegrain style reflector. Totally don't have time to tell you what the hell that means, but let's look at a picture of it here. It looks, let's go to large images. What's going to limit the amount of diffraction we can get? Here's a, do I have any good pictures here? I'd like to see a picture where we can see the opening of the telescope. So here's a 1,000 pixel image. That works for me. You guys can see here, this is the opening of the telescope tube. That's its aperture. And astronomers usually try to make the aperture the same size as the diameter of the mirror below. The aperture does get a little bit blocked by the secondary mirror, but that's a story for another day. Basically, the diameter of this telescope is 16 inches, which translates to about 0.4 meters. It operates, obviously, at optical wavelengths because it's meant for people to look through and enjoy the nighttime sky. So what I want to do is this. Find the diffraction limit of the CCRI 16-inch 0.4 meter telescope. We down with this? The wavelength of observation is optical. So what do you think would be a good number to use for optical wavelengths? Lovers of the electromagnetic spectrum.
Nanometers?
Well, how many nanometers, Jace?
Sorry, what was the question?
The question is, I need a wavelength to plug into this formula, and I need that wavelength to represent optical. My telescope does not operate in the ultraviolet or the infrared, so I can't put in 10 nanometers here. I need to have a reasonable guess.
Like 500 nanometers?
Love it. What does nanometer mean again? Nanometer means what in terms of powers of 10? Can someone help me convert that to meters?
500 times 10 to the negative 9.
Thank you. All right, let's calculate our diffraction limit. Our minimum angle of resolution is 250,000 arc seconds times 500 nanometers divided by the diameter of my telescope, 0.4 meters. Punch and crunch, students. Hey, Jordan. Jordan, could you turn down to like the
How tiny an angle?
Y'all got an answer for me?
My detector can.
What's up with your detector? Don't make me punch this, guys. That's not my job.
Is it 0.3?
That's what I got too.
Minutes, Tina?
Seconds?
Arc seconds, right. I wish my telescope could see down to 0.3 arc seconds. That would be the shit. If it could see down to 0.3 arc seconds, my telescope would be what was called diffraction limited. Diffraction limited means my telescope's ability to resolve features.
I have a quick question. That
Sure.
is not what I got.
Okay, so let's punch again together. Chrissy, here's how I'm doing it.
Yeah.
Watch me and follow my moves.
Right, hang on.
Sometimes you can put the wrong number of zeros in, so I'm going to do 2.5 exp5 instead of typing in 250,000 times 500 exp minus 9 divide by 0.4. And I got their number. Maybe you put the wrong, yeah, you're good now. Okay, cool. Class, in reality, my telescope is not limited by diffraction, but it's limited by something called sky seeing. And that's because my telescope has to look up into outer space through a fluid called our atmosphere. And light traveling down through our atmosphere is subject to distortions which bend and twinkle the starlight, and they limit my minimum angle of resolution usually to somewhere between 1 and 3 arc seconds. Now, if sky seeing doesn't make a lot of sense to you, I can sort of show you what I'm talking about a little more visually here. On YouTube, there's a couple of nice pictures of, or videos of astronomical seeing. It only lasts a few seconds, so you got to watch closely here. Notice that in this, hold on. Come on, internet. Notice in this loop that someone took of a person observing Jupiter, can you see how the image of Jupiter looks wavy like it's underwater? That's the turbulence of our own atmosphere distorting and bending the light as it travels to our telescope tube. This is why my telescope cannot actually see 0.3 arc seconds of resolution. The atmosphere kind of warps and whoopies, almost kind of like one of those mirages that you see in the desert. It's the turbulence of our atmosphere. The molecules are capable of bending light around, and that smears the light out over a 1 to 3 arc second angle. In other words, my telescope would work a lot better on the moon than it would on Earth because the moon doesn't have an atmosphere, right? I'm limited by our atmosphere. I'm not, I wish I was diffraction limited. Now, assuming that I can see down to 1 arc second or so, let's say I even could take the atmosphere away from Earth so I could improve my telescope seeing. Could I resolve the American flag on the moon if I could see 0.3 arc seconds? Well, the answer to that question can be computed with the small angle formula part 2, which I taught you earlier in this lecture. So here's the moon, and here's a feature that I would like to resolve, like a crater. And I'm looking at it from Earth about 384,000 kilometers away. Let's imagine that I could see down. Here's my telescope over here. And let's imagine that I was diffraction limited and I could see a feature that was 0.3 arc seconds across. The distance to the moon is 384,000 kilometers. If we call the size of the smallest feature I could see S, the small angle formula would let us calculate how big that is. It's 384,000 kilometers times 0.3 arc seconds, all divided by 206,265 arc seconds. Go ahead and plug that in for me, students. Kayla?
I guess you'd round to 0.6
0.6 what?
kilometers.
Yeah. That's a half a kilometer. So Kayla, why can't your grandpappy see the American flag on the moon when he comes to visit my telescope?
It's too small.
Yeah, it's too small, and telescopes are limited by diffraction. The size of the American flag is like 2 meters by 3 meters that they left on the moon. You can look it up under Lunar Flag Assembly on Wikipedia if you're curious. Okay. You guys got those notes? Let's take a step back. At this point, we are done with our lecture. In a moment, I'll stop recording. Unfortunately, our lecture is going to be broken into 2 parts for anyone watching later. That's irritating. Maybe my friends can help me. Maybe I'll find a cheap video editor to glue it back together. It's now time to do our homework, correct? Okay. We're going to crank through today's homework. It's not too hard. We're all trained for it. My cat heard lecture was over and promptly scrammed. Okay, so guys, let's take a 2 to 3 minute pause. I'll get a glass of iced tea, and then we'll start the homework. Does that sound like a plan? Okay, I'm going to stop the recording.